Okay, so I should probably first go ahead and share my screen. You move the recording. Okay. Oh. All right, so recall that last time we were talking about moment generating functions, and you have already seen moment generating functions a little bit in that you have learned how to compute some moment generating functions for various continuous and discrete random variables. So what's a moment generating function? So suppose X is a real valued random variable.
So are you sharing your screen?
Oh, I'm such an idiot. Thank you for letting me know. Sorry. Sorry. I am stupid. Okay, 1 second. I need to do that. Thanks, Ayush, right? Trying to recognize voices.
Right, right, sir.
Share screen. Sorry about that. Okay, here we go. Much better. Now you can see everything. Okay, and you can hear me well. Okay. Okay, so last time we were talking about moment generating functions. So let's just recall what's going on here. So suppose we have X, which is a real valued random variable on omega FP with law mu. You have seen this definition before. The moment generating function of X is given by M of S is expectation e to the Sx. All right. And of course, you can write it this way in terms of the law mu. And the domain of M is the set of all S in R for which this expectation or integral is finite. We have seen examples for which the moment generating function, for any random variable, M of 0 is going to be finite. But other than that, you may have situations where M of S is not finite for all possible S's. Anyway, one thing we saw last time is that we went through the details of it and we saw that the moment generating function for any random variable has to be defined on an interval. Okay, 0 is going to be there in the interval. The interval may be 0 and everything to the left. It may be 0 and everything to the right. It may be some interval which actually contains 0 and a little bit to the left and the right, and it may be the whole real line, but it has to be an interval containing 0. Okay, we went over this in detail. Then we talked about why is it called moment generating function. Then we just played around a little bit, and it seemed like if you take the nth derivative of this moment generating function and you plug in S equals 0, you should get expectation x to the n. Now, of course, some technical assumptions are needed. But if those technical assumptions are in place, then you can basically get all the moments by simply taking derivatives and plugging it at S equals 0. Then we were looking at a particular proposition. This proposition said, suppose I have X, which is a real valued random variable on omega FP with law mu. Suppose that MS equals expectation e to the Sx is defined for all S in some interval minus S0, S0. So it's defined for in some open interval containing 0. Then the claim is that X has finite moments of all orders. And further, M of S can be represented as a Taylor series in this fashion. And the Taylor series coefficients are Ex to the K divided by K factorial. That's the coefficient for S to the K. We went through the proof of this last time. There was one hole here, right? And the one hole had to do with, we said expectation sum K going from 0 to infinity, S to the K, X to the K over K factorial equals the sum K going from 0 to infinity, S to the K over K factorial expectation X to the K. This needs a little bit of justifying. Now remember, if X, this needs justifying. If you were talking about purely non-negative function, then you are adding them all up and you are taking expectation, no problem. Expectation of sum is sum of expectations, because the worst case scenario is you'll get infinity. But when there are terms that could potentially be of different signs, you have to be careful just to make sure you don't have infinity minus infinity everywhere. So to fill in this gap, we needed a certain lemma. Let's go over that lemma. Okay, so the lemma says the following. Suppose omega FP is a probability space. Suppose y and n greater than or equal to 1 is a sequence of random variables. And suppose that if I take the sum n greater than or equal to 1, expectation, absolute value of yn, I get something finite. Okay, so I have a sequence yn, n greater than or equal to 1 of random variables. And if I take the absolute value of each yn, if I take expectation and I add up all the expectations, let's say I get something finite. The lemma then says that the sum n going from 1 to infinity yn converges absolutely, p almost surely. Now, just a reminder, this is something from calculus or real analysis, however you want to think of it. Suppose I have a series of real numbers, sum n going from 1 to infinity xn. I'll say that this converges absolutely if sum n going from 1 to infinity, absolute value of xn is finite. Okay. So I'll say a series converges absolutely if, instead of taking the terms of the series, I take the absolute value of each of the terms and I add them up, and I still get something finite. Then I'll say that that series converges absolutely. All right, so in this lemma, we're saying that under these assumptions, the sum n going from 1 to infinity yn converges absolutely, p almost surely. So that means p almost surely, this guy converges absolutely. If this guy converges absolutely, that means that if I take the absolute value of the yns and I add them all up, I will get something finite. Okay, so once again, I'm starting with omega fp, which is a probability space. Okay, I have yn n greater than or equal to 1, which is a sequence of random variables. Nobody has said anything about them being non-negative. Okay, so then potentially could take both sides as a sequence of random variables such that if I take the sum over all random variables of expectation absolute value of yn, I get something finite. The claim then is that the sum n going from 1 to infinity yn converges absolutely, p almost surely. That means you can throw away a set of probability 0, and once you have done that, on whatever is left, this thing is true. Okay, so the claim is that this series converges absolutely, and further that it is integrable. And finally, the expectation of the sum is the sum of the expectations. That's what we're claiming here. And again, if all the yns were non-negative, then we would not need to say all this because we have already sorted those kinds of issues out, right? If yns were non-negative, then you know expectation of sum is sum of expectations, no problem. But here the yns may take different sides. Okay, so here's the proof. All right, so what do we know? We know that expectation sum n going from 1 to infinity absolute value of yn is the sum n going from 1 to infinity expectation absolute value of yn. Why is this line true? This line is true because we're talking about non-negative random variables, right? For non-negative measurable functions, integral of a sum is a sum of integrals. So for non-negative random variables, expectation of a sum is a sum of expectations. In this line that I'm indicating here with that arrow, we're dealing with absolute value of yn, which is non-negative, absolute value of yn, which is non-negative. Okay. So expectation sum n going from 1 to infinity absolute value of yn is sum n going from 1 to infinity expectation absolute value of yn. Okay, now what was the assumption? The assumption was that this quantity that I've just circled is finite. Therefore, the left side must be finite since the two are equal. So what does that mean? That means expectation sum n going from 1 to infinity absolute value of yn is finite. Now I will use a simple fact. Use the following fact. Can somebody complete this for me? Suppose the integral of absolute value of f d mu is 0, then what must be true?
F is 0 almost everywhere.
Right,
F will be 0, mu almost everywhere.
F has to be 0 almost everywhere, right? If you translate it into random variables, what you're saying is Suppose I'll use a different letter here. Suppose expectation absolute value of z is finite. Oh, no. Sorry, I'm sorry. That's not what I want. This is the true statement. What I wrote down is true. It's not false. But this is what I actually wanted to say. Suppose integral absolute value of f is less than infinity, then what can you say? Then you know that absolute value of f must be finite almost everywhere, right? We did this when we did integrals. If a non-negative function has finite integral, then if at all it takes the value infinity, that must be happening on a set of measures 0. Similarly, if I have expectation absolute value of z is less than infinity, then what must be true is that absolute value of z must be less than infinity almost surely. Okay. So where are we? Okay, so expectation sum n going from 1 to infinity, absolute value of yn is finite. So I'm basically saying expectation of this non-negative random variable is finite. So that means the non-negative random variable must be finite p almost surely. So sum n going from 1 to infinity, absolute value of yn must be finite p almost surely. Right, so what is that saying? That is saying that sum n going from 1 to infinity yn converges absolutely p almost surely. Right, and again, that was part of what we were trying to show. Right, sum n going from 1 to infinity yn converges absolutely p almost surely. All right, now we still have to do the second part having to do with integrability. All right, so let Sn be the sum I going from 1 through n yi. Let S be the sum I going from 1 to infinity yi. Can somebody tell me why this S is well defined? This series converges absolutely, almost surely, right? That means if you take this series and you put absolute values here and you sum it all up, it's still going to be finite. Okay. Now, what else do you know? You know that if a series is convergent, then the sequence of partial sums converges to the sum of the series. So Sn converges to Sp almost surely. All right. So now what we'll do is we'll say, let's look at absolute value of Sn. So if you're wondering what's going to come next, dominated convergence theorem is going to come next, right? Because we want to say that expectation of the limit is the limit of expectations. And again, we're dealing with real valued random variables, so we have to be a little careful. So let's look at absolute value of Sn.
So,
Yes.
So how did you say that we can make sure that S will be well defined?
Okay, let's go over that. Do you agree with this? Sum n going from 1 to infinity yn converges. Do you agree with this thing? Sum n going from 1 to infinity yn converges absolutely p almost surely. Okay.
Yes.
So what is this saying? This is saying throw away a set of measure 0. On whatever is remaining, this series converges. Agreed? Now there's just a resultant real analysis which says that if this series converges, then this series is definitely going to be okay. Okay, so if you have this absolutely converging series of real numbers, then the corresponding series is also going to converge.
Okay, so absolute convergence implies.
I'm sorry?
Absolute convergence implies convergence.
Convergence. Exactly. Yes, that is how you would summarize it. Absolute convergence implies convergence.
Sure, sir.
All right, so that's why off of a set of measure 0, maybe you may have to throw away a set of measure 0, but once you do that, S equals sum I going from 1 to infinity yi is well defined. Now, what do you know? You know that Sn converges to Sp almost surely. Maybe you had to throw away a set of measure 0, but on whatever is left, Sn is converging to S. Now, absolute value of Sn is the absolute value sum yi I going from 1 through n. Now remember, these are finite sums right here. So I will use triangle inequality. Absolute value of the sum is less than or equal to sum of the absolute values. So absolute value of the sum is less than or equal to sum I going from 1 through n absolute value of yi. Now remember that here I have absolute value of yi, so these guys are non-negative. So as I make this index n bigger and bigger, the result cannot get smaller. In other words, sum I going from 1 through n absolute value of yi is going to be less than or equal to the sum I going from 1 to infinity absolute value of yi. Right? Because when you have a series with non-negative terms, the more terms you add, the bigger it gets or it stays the same. All right, so you have absolute value of Sn less than or equal to sum I going from 1 to infinity absolute value of yi. And what do we know? We already know that expectation sum I going from 1 to infinity absolute value of yi is finite. So now we can use dominated convergence theorem. The sequence Sn converges to S. The sequence Sn is integrable. Sn is dominated by this guy, and this guy is integrable. So you can use dominated convergence theorem and say integral of the limit is the limit of the integrals. Questions? All right, so that's what I've done here. So this is LDCT. This is, of course, Lebesgue dominated convergence theorem. All right, so by Lebesgue dominated convergence theorem, what you have the desired claim, which is that expectation sum I going from 1 to infinity yi. Remember that this is simply S. Is going to be the limit n goes to infinity, sum I going from 1 through n expectation yi, which is the sum I going from 1 to infinity expectation yi. And this is exactly what we wanted to prove. Any questions? Questions? So this is the lemma that you need to plug in that hole that was there in that theorem we did earlier. Okay. So the next thing we need to talk about is, okay, so this is also related to independence, and it has to do with certain theorems. So basically, where I want to go with this is the following. Okay. So I have G and H, which are sub-sigma algebras of F. Okay. I know what it means for G and H to be independent. Now, if I want to check that G and H are independent, I should check that for every set in G and for every set in H, probability of the intersection, the product of the probabilities. Okay, but now you say, is there an easier way to do it? Do I need to check it for every set in G and every set in H, or is there an easier way? So this lemma is saying that sometimes there is an easier way. So it says that suppose I is a pi system which generates the sigma algebra G, and J is a pi system that generates the sigma algebra H, and let's say I and J are independent, then you can be sure that G and H are independent. So this provides a way of checking something by doing an easier check. Now, of course, at this point, you may not know what pi system is. That is what we plan to talk about. Okay. So this is one way we will use the results we're talking about. Now, I just want to mention that we'll encounter a few terms. We've already encountered sigma algebra. Okay. We're going to encounter next a pi system. I mean, if you're thinking in terms of animals at a zoo, a sigma algebra is one type of animal, and a pi system is another type of animal. There's something called a D system, which is the third type of animal. They're all animals. They're all related to each other. So sigma algebra is actually a pretty strong property. If it's a sigma algebra, it's definitely a pi system. If it's a sigma algebra, it's also a D system. So pi systems and D systems are somewhat weaker, but let's see what they are. This is where we're going with all this. Okay, so if you're wondering why is all this coming up, you can say, okay, here's one motivation. To check that sigma algebras G and H are independent, I know what I should do. I should check that for every set in G, for every set in H, probability of the intersection is the product of the probabilities. But is there a quicker way to do this? The answer is, suppose I and J are pi systems, whatever that means, such that the sigma algebra generated by I is G and the sigma algebra generated by J is H. And suppose I and J are independent, then you can be sure that G and H are also independent. Okay, so this is what we're kind of going towards. Another use of this is the following. So right now I'm just giving you some motivation why we're talking about pi systems, why we will be doing certain theorems. So one motivation I already gave you about independence. So here's another motivation. So suppose S is a non-empty set and okay, so maybe here the question is this. So suppose S is a non-empty set and suppose script S is a sigma algebra on S. Now I know what it means for the measures mu1 and mu2 to be equal. Equal means they should agree for every set in S. But I give you less information. I tell you that for every set in some smaller family pi, mu1 of A equals mu2 of A. And the question is, can you conclude that mu1 and mu2 must be the same on the whole sigma algebra? This proposition is giving you some sort of partial answer. So it's saying, suppose S is a non-empty set. Suppose pi is a pi system on S. Suppose the script S is the sigma algebra generated by pi. Suppose mu1 and mu2 are measures on S script S. And suppose they agree on the pi system. And further, suppose that mu1s and mu2s are both finite measures and have the same, give the same mass to S. So mu1s is mu2s is finite. Then mu1 and mu2 must be the same on all of S. Okay. So one way of motivating this is I have a set S. I have a sigma algebra. I have two measures, mu1 and mu2 on it. I don't necessarily know that mu1 and mu2 agree on this whole sigma algebra script S. However, I have a subfamily of script S, which is pi. And I know that on pi, mu1 and mu2 agree. The question is, do they agree on the whole sigma algebra? What this proposition is saying is, suppose this smaller family is a pi system. Suppose the sigma algebra generated by this pi system is in fact script S. And suppose mu1s and mu2s are both finite in the same number, then yes, equality of mu1 and mu2 on pi is enough to ensure that mu1 and mu2 are the same on all of S. So these are two ways to motivate what we're about to talk about. Any questions so far?
So
Yes.
in the previous slide, pi was the sigma algebra for script S, and script S is the sigma algebra for capital S. Is that it?
Okay, so capital S is a set.
Right.
Script S is a sigma algebra on S, and pi is some family of script S.
Okay.
Some subset of script S.
Okay.
Okay. Okay, so now at this point you don't know what a pi system is. So let's see what a pi system is. We'll also run into something called a D system. And then there's also going to be a theorem related to Dynkin, which we will use. Okay, so anyway, that was just some motivation. So suppose S is a non-empty set. What do I mean by sigma algebra on S? Well, a sigma algebra is a family of subsets of S, which is closed under countable unions and under taking complements. That is the definition of sigma algebra. The definition of pi system is, a pi system is a family of subsets of S, which is closed under finite intersections. Okay. So they're both the same type of object, right? You have a set S, you have a set S. You have a family of subsets of S, you have a family of subsets of S. If the family is to be a sigma algebra, you check conditions A, B, C. If the family of subsets is to be a pi system, you'll check condition D, so to speak. All right, So what we're saying is, suppose S is a non-empty set. A pi system on S is simply a family of subsets of S. We're denoting it by capital Pi, which has the property that whenever I take two sets, I1 and I2 belonging to pi, then I1 intersect I2 belongs to pi. Any questions with this? So this is actually much easier than sigma algebra also, right? In sigma algebra, to check that something was a sigma algebra, you had to check that it was non-empty. You had to check that if something is in the sigma algebra, its complement is in the sigma algebra. You had to check that if I have a countable collection of things in the sigma algebra, the union is in the sigma algebra. Here you have to do very little. You just have to check that if I1 is in pi and I2 is in pi, then I1 intersect I2 is in pi. Finished. If that is true, then you call this a pi system. Any questions with what we're saying there? So let's see if I can write down a pi system here. So let S be R, the real line. And let me see if the following is a pi system. What should I do? Let's see if this works. So I'm taking S to be the real line, and I'm taking the family pi to be the collection of all intervals together with the empty set. I think this is going to be a pi system, right? Because if I take any two intervals, their intersection is going to be another interval, or it's going to be the empty set. So if I take any two intervals, and I should allow single points also. Okay. So suppose I take pi to be the collection of all intervals, open, closed, half open, half closed, finite, infinite, whatever, together with the empty set, and together with all singleton sets. Okay, all singleton sets. Then I claim that if I take the intersection of any two intervals, I will either get an interval, I will get a point, or I'll get the empty set. If I take the intersection of a point and an interval, I'll get a point or the empty set. If I take the intersection of 2 points, I'll get a point or the empty set. If I take the intersection of the empty set with anything, I'll get the empty set. So this would be an example of a pi system. All right, so here is the proposition we're working toward. This we already went over, right? So suppose S is a non-empty set, and suppose capital Pi is a pi system on S. Let script S be sigma of pi. Remember, we have talked about this sort of thing. Suppose S is a set and I give you a family of subsets of S. We have talked about what you mean by the sigma algebra generated by that family. That's exactly what we're doing here. So S is a non-empty set. Pi is a pi system on S. All right, let script S be sigma of pi. Suppose I have measures mu1 and mu2 on S script S, such that mu1 and mu2 agree on pi. And further, that mu1 of S equals mu2 of S is finite. Then the claim is that mu1 equals mu2 on all of S. All right, so that's what we're working toward. So far, so good. All right, so now we know what a sigma algebra is. We know what a pi system is. Now, a third kind of animal that we'll deal with is something called a D system. So let's see what a D system is. Okay, by the way, before I go any further, is a sigma algebra a pi system? Sanjukta? Sanjukta?
Yes, sir. Yes.
It is a pi system, right? Because the sigma algebra is actually closed under countable intersections. It's definitely closed under finite intersections. So every sigma algebra is a pi system. Okay, well, let me actually put it in a slightly clearer language. Every sigma algebra has a pi system. If something is a sigma algebra, it has to be a pi system. Okay. Now we're going to define another type of family of subsets of S called a D system. Let's define that. So let S be a non-empty set, and let script D be a collection of subsets of S. All right. Now I will say that script D is a D system on S if the following things are true. First of all, the whole set S should belong to D. Second, if A and B belong to D and A is sitting inside B, then B minus A must belong to D. And third is, if I have A and n going from 1 to infinity, which is a sequence in D, with an contained in an plus 1 for all n, then the union A and n going from 1 to infinity must be an element of D. Any questions with what we're stating? All right, so just to be clear, the set we're working on is capital S. So capital S is some non-empty set. Okay. Script D is a collection of subsets of S. Okay. We will say that script D is a D system on S if the following things hold. The first thing is that the whole set S is an element of D. Second is if A and B belong to D and A is sitting inside B, then B minus A is an element of D. And third, if an n going from 1 to infinity is a sequence in D with an contained in an plus 1, then the union of all the ans is in D. So here's a question. Okay. No. That's what I'm not omega, sorry, yes. Consider this family. D equals the set containing S and the empty set. Is this a D system? Rishikesh, Pawar, is this a D system? Dhiren Maheshwari, is this a D system?
Yes, sir.
Yes, sir.
Yes, it is.
Yeah.
It is.
Right, it is, right? The first condition is that S should belong to D. Check. S is there.
Hmm.
Second condition is if A and B belong to D and A is sitting inside B. Okay. Then B minus A must belong to D. So suppose I take A to be S and B to be the empty set. Then the requirement is that the difference, which is S, should be in the family, which it is. Suppose I interchange the roles of A and B, same thing. Suppose I take A to be S and I take B to be S. Okay, so let me do the following. So suppose I take A is S, B is the empty set, A is the empty set, B is S, A is S, B is S, A is the empty set, B is the empty set. Right? I mean, this is simple enough that you can list all the possibilities. Right? So for part 2, what are you saying? Suppose A and B belong to D, and A is a subset of B. In the first case, is A a subset of B? No. Right? S is not a subset of the empty set. By the way, just to this is just a reminder about basic mathematical logic. I mean, just basic reasoning about proofs. Suppose I make a statement P implies Q. Okay. If P is false, then the statement is automatically true. Right? You know that. right? I mean, you guys remember that from basic analysis and set theory, right? If I have a statement P implies Q and the first part is false, then the statement is true because all the statement is saying that if P is true, then such and such should happen. But if P is already false, then you're fine. There's nothing to check. Okay. So what I'm getting at is, suppose A is S, B is the empty set. So is A a subset of B? No. So nothing to check. Consider this possibility. A is the empty set, B is S. Is A a subset of B? Yes. What is the difference? B minus A is S. So the requirement is that B minus A should belong to D. Yes, S belongs to B. Suppose A is S, B is S. Is A a subset of B? Yes. The requirement of property 2 is that B minus A should be in D. Well, B minus A is going to be S minus S, which is the empty set, which is in D. Correct. And of course, is the empty set a subset of this? I guess you would say yes, because empty set is a subset of something whenever if X in the empty set, then X in whatever set. But if X in the empty set is always false, that is going back to what I was saying here. A statement P implies Q. If P is false, the statement is true. Anyway, are you guys with me so far? So for this particular simple example, we have checked 1 and 2. You guys with me?
Yes, sir.
Do you think 3 will hold? I don't have the patience to write it all down, but do you think 3 will hold? It's going to hold, right? So I'll leave it to you to just think about it. The 3 is also going to hold. This D is a D system. Is it a sigma algebra? Because?
Yes, sir.
Yes, it is, right?
Yes, sir.
The simplest sigma algebra always has the empty set and everything, nothing and everything. That's always a sigma algebra.
So it is the smallest sigma algebra.
Exactly. It is the smallest sigma algebra on the set S. Yes. It's also sigma algebra. And you know that every sigma algebra is a pi system. So this is also a pi system. Okay, next thing I want to ask you is suppose I have a sigma algebra. Is a sigma algebra a D system? Let's change color here so that you can no, let D be a sigma algebra. Well, let me just go with S, right? We've been using S for sigma. Let S be a sigma algebra on S. Is S a D system?
So not
S-
every time.
Yes, it is, right? It is a D system, right? Because what do you need for, so the sigma algebra always contains the whole set. So S is in D, that's done. Suppose A and B are elements of D. Well, if you take any two guys in a sigma algebra, A and B, B minus A is always going to be in the sigma algebra. Whether A is sitting inside B or not is irrelevant. Right? If A and B belong to a sigma algebra, then B minus A is in the sigma algebra. Finished. You don't even need this. Second condition is true. And a sigma algebra is closed under countable unions. So of course the third condition is true. Because the third condition is saying is that it should be closed under, okay. Can somebody tell me how one could say, express this in words? Let me start the sentence. D is closed under. Complete the sentence. I've written this using symbols, but now I said, suppose I asked you to explain this using words, right? You say sigma algebra is closed under taking complements. It's closed under taking countable unions. Okay. So somebody, can you tell me in words, how would I describe this property 3?
Closed under countable union of monotony increasing sequence of sets.
Right. So it's closed under countable increasing unions. Let's say that. Right. What you said is correct. I'm just trying to think if we can throw what's the minimal. It's closed under countable increasing unions. Yeah, I think you can say that. It's closed under countable increasing unions. All right.
Yes, sir.
All right. So now here are a couple of propositions. So let's start with this. So suppose S is a non-empty set. Now I claim, now we were wondering about the relationship between various things, right? Sigma algebra is pretty strong. Sigma algebra implies pi system, sigma algebra implies D system. But now the nice thing here is the following. Sigma algebra, if and only if both pi and D system. So sigma algebra implies pi system, sigma algebra implies D system. If on the other hand, you check that it's a pi system and D system, then it is a sigma algebra. So that's what we're saying here. Let S be a non-empty set. A collection script S of subsets of S is a sigma algebra if and only if S is both a pi system and a D system. Okay, so sigma algebra if and only if pi system plus D system. Okay. Do you agree that one direction is trivial? Which direction is trivial? Poonam?
So if it's a sigma algebra, then it will be a pi system and D system.
Right. So that we already did on the previous page, right? So I think hopefully you will all agree with me that this statement is kind of trivial. If S is sigma algebra, then it is both a pi system and a D system. We already scribbled this on the previous page. Okay, by the way, before that, let script S be a collection of subsets of S. Okay. Clearly, if script S is sigma algebra, then it is both a pi system and a D system. That we already did our scribbling. We know the answer is true. So far, so good. Okay, so now what do we want to do? Now, suppose that script S is both a D system and a pi system. We want to show that script S is a sigma algebra. All right, so one thing at a time. First of all, I claim that the whole, okay, whenever I say the whole, okay, I just want to space. Whenever I use this term whole space, I'm talking of the set in which the action is taking place. Okay, whenever I say whole space, I mean S. Okay, so let's come back here. So the whole space is in script S. Why is this true? Because script S is a D system. So the whole space is in script S. All right, so all right, so that is fine. Now let's look at, now suppose n going from 1 to infinity is a sequence in script S, and suppose A is in script S. To show sigma algebra, what do we need to show? We need to show that union n going from 1 to infinity an is an S. We need to show this. And we need to show A complement is an S. Okay. So suppose n going from 1 to infinity is a sequence in script S. Suppose A is an S. We want to show that the union of all these guys is an S. And we also want to show that A complement is an S. Okay, so let's okay, so let me do the following actually. Well, let me just sneak in a note here. This is what we need to show. We need to show that A complement is an S, and we need to show union n going from 1 to infinity, an is an S. All right, so let's get started. So A is an, so suppose, okay, so by assumption, A is an S. Right? Now, what is A complement? A complement is S minus A. I think we'll all agree with that, right? The complement of a set is everything that is not in the set. Now I will say A is a subset of S. And A is in the D system, S is in the D system. So S minus A must be in the D system. Okay, so I want to show, I have A in S. I want to show that A complement is an S. So I start by noting that A complement is S minus A. Then I note that S and A are both in the D system. Then I note that A is a subset of S. And so by definition of the D system, S minus A must be in the D system. In other words, A complement must be in the D system. Right? So A is in S is in S, and A is a subset of S. Since S is a D system, A complement is in S. Any questions so far? So for the sigma algebra part, we're done with showing that it is closed under complements. Now we have to show that it's closed under countable unions. Okay, so what we'll do here is we'll first show that it's closed under a union of two sets. Then we'll show that because it's closed under a union of two sets, it's closed under any finite union. And then we will show that if it's closed under any finite union, then it must be closed under a countable union. Okay, so first step is show that if A1 and A2 are in S, then A1 union A2 is in S. If you do that, then you can show that if A1, A2 through AN are in S, then the union of all of them is in S. Then you extend it for union I going from 1 to infinity. So that's the plan. Right, so let's first show A1 union A2 is in S. So let's see what A1 union A2 is. Do you agree that any set is whole thing minus the complement of that set? That's what I've written here, right? Any set is whole thing minus the complement of this set. That's just by definition. If you need a cup of coffee to see that, that's fine. But I'm sure that if your brain is even slightly stimulated, you'll be able to see this. This is just almost a tautology, right? A set equals the whole thing minus the complement of the set. All right. So A1 union A2 is S minus the complement of A1 union A2. Okay, then I'll say that the complement of A1 union A2 is A1 complement intersect A2 complement. So A1 union A2 is S minus A1 complement intersect A2 complement. Do you guys agree with this much?
Yes, sir. By De Morgan rule.
What's that?
By De Morgan rule.
Ah, yeah.
By
Right. I've used De Morgan's laws, right. And now I'll say, wait, A1 is an S, so A1 complement is an S because I've already shown closed under complements. A2 is an S, so A2 complement is an S because I've already showed closed under complements. So A1 complement is an S, A2 complement is an S. Now the extra piece of information we have is that S is a pi system. So since S is a pi system, A1 complement intersect A2 complement is also an S. All right, so now what I'll do is I will say, so now let's look at so A1 complement intersect A2 complement is an S, but now we have shown that S is closed under complements. So complement of A1 complement intersect A2 complement is an S. Now let's unwrap this. This guy is S minus A1 complement intersect A2 complement, right? But remember what this is. This is just A1 union A2. So what we're saying is that A1 union A2 is an S. Any questions? All right. So now you can prove by induction that for any finite number capital N, the union of n going from 1 to capital N is an S. Okay, that's not hard to do. If it's closed under a union of 2, it's closed under any finite union. It still does not take care of the closed under countable unions. It only takes care of finite unions. Now we still have to deal with the countable unions. So far, so good? All right. Now remember, there was this third property of D system that I don't think we have made use of yet. Right? The third property was the D system is closed under countable increasing unions. Yeah. Or rather, and the unions of a countable family of non-decreasing sets, whatever. Okay. So here's what I'll do. By the way, can you tell the difference between this and this in my handwriting? Because the difference is important. The first one is the set of natural numbers, okay? With this funny n, this is the set of natural numbers. This is just capital N, which is referring to some positive integer. Okay, so here this is the second one, it's capital N. All right, so let Bn be the union An, going from 1 to capital N. And let B equal the union of An, going from 1 to infinity. I can certainly form these sets. I don't know whether they are in the family S or not, but I can certainly form them. But now wait, about Bn, I know that it is in S. Why do I know that? I have shown here that if I take the union of any finite number of Ans, the result will be in S. But this quantity, the union, n going from 1 to capital N An, is simply what we're calling B capital N. In other words, we know that for each n, B capital N is an S. Any questions so far up to here? This is true because we have shown that S is closed under finite unions. Now we're trying to graduate from there to countably infinite unions. Okay, so now we'll use this third property of the D system about being closed under countable unions of the increasing family. Let me ask you, in our notation, is An contained in An plus 1? Here, is An contained in An plus 1? Right here, I took a sequence An. Is An contained in An plus 1? Do I have any reason to believe that? No, I have no reason whatsoever. That property is not going to be applied to A. It's going to be applied to these guys. It's going to be applied to these. Yes, the ANs are not sitting inside each other. You have no information about that. But the BNs are sitting inside each other. B1 is sitting in B2, B2 is sitting in B3, B3 is sitting in B4, and so on, and all of them are sitting in B. All right. So Bn is union n going from 1 to capital N An. B is the union n going from 1 to infinity An. The Bn's keep getting bigger as n gets bigger. Okay, so what do I know? I know two things. I know that for each natural number n, Bn belongs to S because I've shown closed under finite unions. I also know that Bn is contained in Bn plus 1 for every natural number n. Okay, and so now the third property of D system tells me since S is a D system, the union n going from 1 to infinity, Bn is an S. But now you stare at this and you ask yourself, what is this? B1 is A1. B2 is A1 together with A2. B3 is A1 together with A2 together with A3. So B1 union, B2 union, B3 is just A1 union, A2 union, A3. And when I take the union of all the B's, I'm just taking the union of all the A's. Another way to see that is, suppose I take n going from 1 to infinity Bn, that is going to be union n going from 1 to infinity, union n going from 1 to capital N. And there is a lot of repetition here, but when you put all these together, you just get union n going from 1 to infinity An. So what you get is union n going from 1 to infinity An belongs to S. So yes, S is closed under countable unions. And that is the only thing left to prove that S is a sigma algebra. Any questions for this?
So
Yes.
if we look at it broadly, for a D system, the property that we had is the sets are closed under countable unions if one set is contained inside the other. So this.
One second, let me just add that. Yes, if in a D system, if I have a countable collection of sets and one sets are sitting inside each other, and each of them belongs to the D system, then the union belongs to the D system. Correct.
Right, sir. And for sigma algebra, need for one set sitting inside the other is not there, right? So
exactly. There's no assumption. If I have any countable collection of sets in the sigma algebra, put them together, it should be in the sigma algebra.
Right. So how did we get rid of that part, like from the using the property that it is a D system? how did we get rid of the part that we don't require one set sitting on the inside
Okay.
the other?
Here's how we got rid of it. Roughly. Okay. Okay, Ayush, you want to put together A1, A2, A3 up to A infinity, right? Like, there's no A infinity, but you want to put them all together, right?
Right. So,
So now I'll take B1 to be A1. I'll take B2 to be A1 union A2. I'll take B3 to be A1 union A2 union A3, and so on. Agreed?
agreed, sir.
If I take the first 10 B's together, do you agree that I get the first 10 A's?
Yes, sir.
And if I put all the B's together, do you agree that you get all the A's put together?
Yes, sir. Yes,
And do you agree that the B's are one sitting inside the other?
right, sir.
So that's how we got around it. I think that was your question, right?
Yes, sir. So in the unions that we are doing,
Oh, one second. Oh, hang on. What?
that we are doing, so there are a lot of redundant unions, right? Inside them.
Exactly. What we got here is a lot of redundancy. For every n, A1 is showing up in all of them.
Right, sir.
And then leaving n equals 1, A2 is showing up in all of them. And leaving 1 and 2, A3 is showing up in all of them. Yes, so there is a lot of redundancy here. Correct.
Got it, sir. Thank you, sir.
Okay, so this proves that S is a sigma algebra. Any questions with this? All right, so now eventually I want to get to this thing called Dinkin's lemma. This thing I'm not going to prove. I'm saying here, please see MA 514 notes. I'm happy to share the notes with you, but I don't want to go through this. I will end up spending a lot of time doing this, but I would prefer to just state it without proof and use the results. But before that, I need some definition. Okay. So once again, of course, I have some set S. Okay. Now, suppose script C is a class of subsets of S. Okay. I'm going to define D of C as follows. I'm going to define D of C as the intersection of all D systems on S which contain C. Does this remind you of anything? Sigma algebra generated by a family, right? Sigma algebra generated by a family is the intersection of all sigma algebras which contain that family. And there's always at least one sigma algebra which is the power set. So similarly, if I give you C, which is a family of subsets of S, is there a D system which definitely must contain C? Yes or no? Yes, right? The power set.
So could you repeat the question?
Sure. S is a non-empty set. Let C be a collection of subsets of S. Is there a guarantee that there is at least one D system which contains this family?
Yes, sir.
Yes.
The power set.
The power set. Yes. So what I'm saying is there's always going to be at least one D system which contains this family. Anyway, so now we're going to define D of C to be the intersection of all such D systems. Okay. So S is my set. C is a family of subsets of S. D of C is the intersection of all D systems on S which contain C. And there's at least one such, namely the power set. All right, so I will not go through this. Okay, so I'm making a claim here. I'm making a claim here that if I take an intersection of D systems, I will still have a D system. I am not going to go through the proof of that. Does this ring a bell? We did this for sigma algebras, right? We said if you have any family of sigma algebras, you take the intersection, it will still be a sigma algebra. I'm making the same type of statement. I'm taking an intersection of a bunch of D systems, the result is still going to be a D system. So in other words, it's easy to check that D of C is in fact a D system. It is also the smallest D system on S containing C. Right? Why is it? Because it is the intersection of all D systems containing C. All right, so you might say DC is the D system generated by C. So far, so good? Yes? No? Okay. Now I'm going to make another claim here. D of C is contained in sigma of C. Do you guys agree with that? So C is a family of sets. D of C is smallest sigma algebra. No, not sigma algebra, sorry. Smallest D system containing C. Agreed? Suppose I look at sigma of C. We have seen that every sigma algebra is a D system. So sigma of C is a D system containing C. Well, if this is a D system containing C, then the smallest D system must be contained in sigma of C. That's how I got this, D of C contained in sigma of C. Left-hand side is the smallest D system containing C. The right side is a sigma algebra containing C. And every sigma algebra is a D system, so it is a D system containing C. So the right side is a D system containing C. This is the smallest D system containing C, so this containment must hold. Questions so far? All right, so now here's our claim. All right, so here is Dinkin's lemma. Let S be a pi system on S, then D of S equals sigma of S. Okay, so what we're saying is that any D system that contains a pi system also contains the sigma algebra generated by that pi system. Okay, right. So what are we saying here? S is our set. Suppose script S is a pi system on S. Then the claim is that D of S is sigma of S. Now remember, you already have D of S contained in sigma of S. That is already there. Now this is giving you containment in the other direction. Do you guys agree with that? Here we had S, we had a family of subsets. And for this family of subsets, D of that family was contained in sigma of that family. That is always true. What Dinkin's lemma is saying is that if C is a pi system, then the other containment also is true. Right? So Dinkin's lemma is saying that if C is a pi system, then D of C contains sigma of C. In other words, the two are equal. So that's what we're saying here. So let S be a pi system on S, then D of S equals sigma of S. So let's just make a note. Always have ds subset of sigma of S, regardless of whether S is a pi system. Right? But what Dinkin's lemma is saying is that if S is a pi system, then D of S actually contains sigma of S, and so the two are the same. Okay. So what is the second part saying? It's saying that any D system that contains a pi system also contains the sigma algebra generated by that pi system. All right, let's look at this. So what are we saying here? Here, D of S is a D system. Okay, so here I've stated it in words, and you may be wondering, what does this mean, right? So let's take this thing that's written here in words and dissect it and understand it in symbols. DS is a D system which contains the pi system S. Hence, DS also contains the sigma algebra generated by that pi system. Okay, so let me do the following. Somebody may ask me, I have that statement which is highlighted in green. Can you illustrate what that is saying here? So the statement in green says that if you have a D system which contains a pi system, then the D system must contain the sigma algebra generated by the pi system. So now somebody's question is, okay, I read that thing in green. Can you explain to me in symbols what's going on? Answer is, in symbols, S is the pi system. DS is a D system which contains this pi system. So this D system, DFS, contains the sigma algebra generated by the pi system. So DS contains sigma of S. Does that make sense? Questions? So if you're wondering what the meaning of the sentence in green is, it is what is now highlighted in blue. In green, you're saying any D system that contains a pi system also contains the sigma algebra generated by that pi system. So what is what here? Here S is a pi system, DS is a D system which contains S, and so DS contains the sigma algebra generated by S. So DS contains sigma of S. But remember, you always have DS contained in sigma of S. That is always there for free. Since we also have DS contained in sigma of S, it follows that DS equals sigma of S. Any questions with this? All right, so I'm not going to go through the proof of this. It is, I mean, we can do it, but I would rather use the time for something else. Okay, so this is an important lemma, and we'll just see how to make use of it for the propositions we talked about. Are you guys with me? Okay. So now let's come back to this proposition, right? We had this proposition earlier. Actually, we started the lecture with this. So what did we say? We said, suppose I have capital S, which is a non-empty set. And suppose I have capital pi, which is a pi system on S. Let script S be sigma of pi. I have two measures, mu1 and mu2 on S script S. And I know that mu1 and mu2 match on the pi system. The question is, do they match on the whole sigma algebra, which is bigger? The answer to the question here is that, well, if mu1 and mu2 agree on a pi system, and the measure of the full space is finite, then yes, mu1 and mu2 must agree on the sigma algebra. Any questions with this, what we're stating? So now I want to use Dynkin's theorem to do this. Okay, all right. So here's the proof. Let D be the collection of all measurable sets. So let the collection of all F in S with the property that mu1F and mu2F agree. Okay. So D is the collection of all measurable sets S, F, for which mu1 and mu2 match up. Now remember, for every set in the pi system, mu1 and mu2 match up by assumption. In other words, pi is a subfamily of D. You guys with me? Okay. So now what I have here is D contains this pi system. Now, if I can show that D is a D system, then it must contain the sigma algebra generated by the pi system, which is script S. So if I show that D is a D system, then D must contain sigma of pi. But sigma of pi is script S. So if D contains script S, that means for every set in D, mu1 and mu2 match. Okay, so that's what we want to do now. We claim that D is a D system on S. All right. So again, to check that script D is a D system, what should you do? You should check three things, right? So first is, I claim that the whole space is in script S. This is easy to see, right? Because the whole space is definitely measurable. Okay, and mu1s and mu2s are the same. So the whole space is an example of a measurable set for which mu1 and mu2 agree. So the whole space belongs to D. All right. Now, suppose A and B belong to D with A contained in B. Right? What do we want to show for D system? We want to show that B minus A belongs to D. Agreed? Now, I can write A is sitting inside B. So I can write B as A union B minus A, and this is a disjoint union. I think you'll agree with that. Now, since this is a disjoint union, I can write mu1b is mu1a plus mu1b minus a. Measure of the whole is the sum of the measures of the parts. Similarly, mu2b is mu2a plus mu2b minus a. Same reason, measure of the whole is the sum of the measures of the parts. All right, now remember that mu1s, mu2s are finite. So mu1a, mu2a, mu1b, mu2b all have to be finite. So since mu1, mu2 are finite measures, mu1 of b minus a, which is this quantity here, which must be mu1b minus mu1a, right, which is mu1b minus mu1a, which is mu2b minus mu2a. The reason for that is that mu1 of b and mu2 of b match up, mu1 of a, mu2 of a match up. So this is mu2b minus mu2a, and this is mu2b minus a. So what have we shown? We have shown that b minus a, well, b minus a is an S. Why is this true? This is true because S is a sigma algebra. So b minus a is an S. And right now we have just shown that mu1 b minus a is mu2 b minus a. So b minus a is a measurable set on which mu1 and mu2 match. So b minus a must be in D. You guys with me? So we've shown the second of the three properties for this guy to be a D system. Okay, the third thing we want to show is that we want to show that it is closed under countable increasing unions. So suppose Fn, n going from 1 to infinity, is a subset of D with Fn contained in Fn plus 1 for all n. Let F be the union n going from 1 to infinity Fn. What do we want to do? We want to show that F is in D. Correct? Okay, now you remember some properties of measures. So by continuity from below, mu1 of F, well, this is just mu1 of the union n going from 1 to infinity Fn. This is just by definition. And by continuity from below, here's by using continuity from below, this is limit as n goes to infinity mu1 union n going from 1 to capital N Fn. So this is true by definition, nothing to it. This is true because of continuity from below. Okay, so I'll get limit n goes to infinity mu1 of the union n going from 1 to n Fn. If I take A1 contained in A2 contained in A3 and I take A1 union A2 union A3, what am I going to get? A3, right? So if I take F1 together with F2 together with F3 together with F4, I'll just get F4. So what I'm saying here is that the union n going from 1 to capital N Fn is just F capital N. So this equals limit n goes to infinity mu1 of F capital N. Also mu2 of F is mu2 of the union Fn n going from 1 to infinity. Why is this true? This is true by definition of what F is. And mu2 of union n going from 1 to infinity Fn is the limit n goes to infinity mu2 of union n going from 1 through capital N Fn. This is true by continuity from below. Okay, and again, the union n going from 1 to 10 of Fn is just F10, right? So this is limit n goes to infinity mu2 of Fn. Okay, so now what will you say? Now you will say that since each Fn is in D, mu1 and mu2 on that set match up. So mu1 Fn is mu2 Fn. But wait, if basically I'm telling you if A1 equals B1, A2 equals B2 dot dot dot, then the limit of An has to be the limit of Bn if both of them exist. So if mu1 Fn is mu2 Fn for every n, then the limits must be the same. But what are the limits? The limits are mu1 of F and mu2 of F. In other words, mu1 of F and mu2 of F are also the same. So F is a measurable set and mu1 F and mu2 F are the same. So F is in D. All right. You guys with me? So what have we shown? We have shown D. Remember, D is the collection of sets where mu1 and mu2 match. B is a D system on S which contains a pi system. By Dinkin's lemma, B must contain the sigma algebra generated by the pi system. In other words, D must contain script S. Now remember that D is always a subset of script S. That is a given. So D contains script S. D is always contained in script S. So D and script S are the same. So what is the defining property of D? The defining property is every set is measurable and mu1 and mu2 match up, which means for every set in S, mu1 and mu2 match up. This is exactly what we wanted to show, right? We wanted to show that mu1 for any set in script S, mu1 and mu2 match up. And so that concludes the proof. Any questions with this? All right, so let's stop right there. Let me stop recording.